Okay, welcome to lab here. We'll get started here, continuing lecturing today, just for a little bit. Just kind of keep us on pace. Okay, so like I said before, we're going to continue lecturing here. We're going to finish up this chapter. We're going to roll into some nuclear chemistry, and then we're going to call it a day, I think. So we finished up at the end of their lecture on this example. Before we continue on and kind of really, I guess, finish this chapter, any questions on what we were doing in this example? And this example really is a very good example of how we can use KSP really to our advantage to, again, do sort of this selective precipitation, and a reminder that that really is sort of the basis of our qualitative analysis experiments. In fact, you'll probably see some calculations in the qualitative analysis experiments where they ask you to kind of use the KSP value to verify whether or not you would expect, a group 2 reagent to come out or a group 3 ion to come out or not to come out and stuff like that. So again, you could use the KSP as sort of to your advantage to really understand sort of the correct concentrations that you need to see a precipitate actually form. So here we sort of talked about in this chapter several factors that affect solubility. And again, there's 3 really major factors that affect solubility is whether or not there's a presence of a common ion. Also, again, as we talked about, the pH of the solution can have a pretty good effect on, especially when you're dealing with acid or base type of substances. And as we sort of finished up here talking about as well, again, concentration is really important as well as to whether or not you would technically see a solid form. So all this just leads you to what we were sort of talking about, that, although we do sometimes have in our heads that the solubility rules are sort of 100%, it is sort of situation specific, and you may not actually see those effects that you see in those solubility rules if something like the concentration is not right, something like pH maybe, or there's some common ions involved. You may actually see some different sort of effects occur. Any questions on any of that there? All right, so just to sort of finish up, we've sort of been talking about it as we've been going through, and we talked officially about it the other week when we did the qualitative analysis experiment. But qualitative analysis really uses KSP and solubility product to take advantage of really our differences in solubility. And when we talk about our qualitative analysis, that's group 1, 2, 3, 4, and 5. And again, a reminder that these are not groups on the periodic table, but these are guys that are sort of placed together based on similar solubility sort of rules, if you will, or similar solubility sort of characteristics. So for example, as we talked about group 1 there, which is our silver, lead, and mercury, those are pretty much our exceptions to the normal solubility of chlorides, bromides, and iodides. And again, that's why those guys are grouped together. That's why, as we talked about, there's a group reagent. So technically why we add that HCl, because that's going to precipitate out those ions as chlorides. When we get to group 2, we can see here we have a lot of sulfides involved, and we do have a precipitating reagent, which is hydrogen sulfide gas. But again, here we see that the pH is really important, because group 2 and group 3 are both precipitated out using the same reagent. So they both are precipitated out using H2S. But the difference really between, again, group 2 and group 3 is, in order for group 3 to come out as solids, you do need to have a basic pH. And really, for our group 2 to come out as solids, you need a pretty acidic pH, something like 0.5 in terms of the acidity. And that will allow those group 2 guys to come out. So here, although we're using the same precipitating reagent between group 2 and group 3, we can't successfully keep those guys separated from each other by controlling the pH. Like we saw in those problems we did earlier, again, the pH is going to allow those group 3 guys, especially when you make it really acidic, to remain in solution, while the group 2 guys will go, cool, I'm coming out as solids. And then obviously once you've finished with group 2, you then can make it basic and add some H2S, and those group 3 guys will come out. As we talked about as well, when you get to kind of group 4 and group 5, you know, some people just do group 4, which includes group 5. Group 5 really is our potassium or sodium or ammonium. Those are guys that are pretty much soluble in everything. So there's really no precipitating reagent for it. But things like barium, calcium, and so forth, there are some precipitation or precipitates that you can make. As you can see there, some carbonates that come out. All right. And we sort of saw the slide earlier. Again, really a lot of this is really the big idea of selective precipitation. And the idea is really for qualitative analysis, as we talked about when we started, is really you have all these ions that are floating around, right? These positive guys floating around. And we want to kind of selectively take each one out at a time as a precipitate. And again, if we do it correctly with the correct reagents, when we do see something like a precipitate, we can know pretty confidently that what we are seeing as that precipitate, or even when we get to the final test for an ion, we have already removed everybody else out of the way, that we can feel pretty confident that what we are seeing is what we expect to see and the ion that we expect to see. And that's why, as we talked about, you know, especially when you get to say like the general unknown or something like that, you do want to do these things in order. So you want to remove all the group 1s. And then when you get to group 2, you can feel pretty confident that, you know, it's just group 2 there. Remove all the group 2s, get group 3, and so forth. So the idea behind qualitative analysis is to, again, carefully remove out everybody until you pretty much have removed everybody but the one ion that you're looking for. And that way, when you run that specific test, you can feel pretty confident that if you do get a positive, that it could only be that ion making that positive. Remember, as we sort of talked about as well, if you decide I'm just going to jump around, I don't really want to remove all the other ions that might be there, remember that as you're adding reagents and you see something occur, what you're seeing occur may not actually be what you think it is, because you had all those other ions that are still floating around that solution that could have potential reactions with what you're adding. Even though you think it's one thing, it may be actually reacting with something else. And that's why it's really that idea of, you know, if I got 3 ions in there, I really want to get rid of 2 of them. And then when I'm ready for my test, I hopefully just have 1 ion by itself. That way, when I do it, I know it is what I expect it to be. Obviously, at the end there, potassium, sodium, ammonium, can't really do a flame test for, but there's a lot of elements that you can obviously do flame tests and look for a specific color of flame that will help you identify it. So for example, sodium is that yellow flame, potassium, a little hard to see here, is usually kind of a purple violet type flame. Copper has that greenish blue type color. And you can see lithium has red, so does calcium has an orangey red type color. All right, any questions on this? So again, this should wrap chapter 16. A reminder that there still is a part of chapter 16, I believe, which does cover complex ion calculations and KF, the formation constant. Again, we're going to skip that for now. We are going to come back to it in a later time when we talk about some other things. Any questions on that there? Okay, let me try this move here. We're then going to go to nuclear chemistry, which again, it should be up there, I think. Okay. Oh, yeah. Okay, so hopefully you should be able to see that, I hope, yes. All right. So we're going to try to make a, the view's okay, I hope, yes. Okay. So we're going to talk here about chapter 19, which is nuclear chemistry, and hopefully make a little dent into it today, I think. So let us get started. So, good talk. Let's go that way. So nuclear chemistry, is it too small? Okay, give me a second. Let me go back the other way then. Hang on one second. Let me just restart it. Sometimes you never know how it switches around. Yeah, let me do this guy. Let me do that. Let me hit that. Let me give you the play-by-play of what you can't see. I'm doing that in case that's helpful to you. I'm closing that. That should be up, I hope, right? And that should be that. And I hope. Okay, let me give this the old try again. Let's do that. Let's do that. Let's do that. And is that better, I hope? Maybe, maybe not. Okay, so better? Good? Okay. Hang on one sec, though. I, of course, am not happy with it, so hang on one sec. On my end. Technology is good, sort of. All right. All right. The old college try number 3 here. Here we go. Let's see. Let's see if I like that any better. I'm not sure. No, it didn't. All right. Is that better for your view at least? Yes. Still good. All right. So we're talking about then radioactivity. Come back. There we go. Okay, so radioactivity is the spontaneous decomposition of smaller nuclei. And obviously, when we talk about radioactivity, anything that goes through radioactive decay, which is basically the sort of spontaneous decomposition of a element, is said to be pretty much unstable. And decomposition sort of occurs as we really a lot of times play with the nucleus and the particles that are in the nucleus. So very different, as we'll talk about here, is in nuclear reactions, as opposed to sort of chemical reactions, we are actually going to be playing with the protons and the neutrons, basically the particles that are in the nucleus. And that's very different than what happens when we have just a basic chemical reaction, right? In a basic chemical reaction, we're dealing with really electrons, right? So we break bonds, we make new bonds. And one thing that we'll talk about, which is really important difference between those two things, is when we do a sort of traditional chemical reaction, because all we are doing is breaking the bonds, we're basically making new bonds on our product side, and we will have conservation of our elements like you're used to, right? We have conservation of elements, which means if you started with 4 carbons on the left-hand side of the arrow, you should end up with 4 carbons on the right-hand side of the arrow. Really, the only difference it's going to be is that they may be in different sort of molecules on the product side. And the major difference between a chemical reaction and a nuclear reaction is, in a nuclear reaction, we do not have that conservation of elements. What we start with in terms of elements and what we end up with in terms of elements are 2 different things. So that is a major, major difference that we have when we deal with something that is a nuclear reaction versus a chemical reaction. Now, when things do go through sort of this radioactive decay, whatever we start with is sometimes referred to as the parent nuclide, which I think is what that says. Might be hard to see on your paper there. And it is the nucleus that is undergoing the change or the reaction that is occurring. And the new nucleus that is formed, the new element that is formed, is sometimes referred to as the daughter nucleus. And essentially, all nuclides above 84 protons are usually radioactive. Now, there is 3 types of radioactive particles that we oftentimes will come across, and that is the alpha particles or alpha rays. And if you remember, alpha particles are those things that Rutherford used when he did the gold foil experiment. They are positively charged radioactive particles, and they do have 2 symbols. We oftentimes will use the alpha symbol, like a 4 and a 2. Or because it really is the helium nucleus, it's very common in nuclear chemistry to also use the helium symbol for it. Now, beta rays or beta particles, they have a charge of -1. They're basically like an electron, which means some people will use the electron symbol with a 0 and -1. And some people will use the beta symbol to represent that. We also have gamma, which is neutral, pure energy. If you remember, like the electromagnetic spectrum, all the way at one end is where you find gamma rays, short wavelength, high energy, right? Gamma rays, pure energy. Is further down on the road there than X-rays, right? So it is very, very high energy when you're dealing with gamma rays. Now, sometimes we also will see some other things emitted in radioactive sort of reactions. Positrons, it's an electron with a better attitude. Thank you very much. Here 4 times a week, 2 shows daily. And that also uses the same symbol, which is the beta symbol. And we'll use that E, but it is a positive, or they will use the beta symbol and the positive one as well. So there is a difference, again, between these two, and the difference is usually for sure displayed when you have a problem. If you just see the beta symbol like that, nothing else written there, it's probably really safe to assume that it is the beta particle, it's the -1. If they are going to do a positron and use the beta symbol or the electron symbol, they will have that +1 there. Sometimes they may even do something like that, but they definitely will indicate that it's a positron rather than just a beta particle. We also will have some type of reaction, which is sometimes referred to as an electron capture, and that's pretty much what it sounds like. Basically, a particle absorbs an electron, and it causes obviously a reaction to occur. So hopefully you remember what some of these numbers sort of mean, right? When we write symbols like we were doing just there, the top number is the mass number. The bottom number on the left there is the atomic number. And hopefully you remember that the atomic number is the number of protons that you find in the nucleus of an atom. If your guy is neutral, it will also tell you the number of electrons, but do remember that the actual definition of an atomic number is what we see here, the number of protons. On the periodic table, that is the top number, is our atomic number. The other thing that you probably remember, hopefully, is it is the atomic number, and that is the number of protons, which is important in terms of identifying what element you are talking about. So if you look at the periodic table, you will see that there is no element that has the same atomic number, which means every single element has a unique atomic number, a unique number of protons, which means you can identify what element you're talking about if you know the atomic number or you know the number of protons, which is essentially the same thing. Now, the mass number is the number of protons and the number of neutrons that you have in an atom. And if you look on the periodic table and this number that's on the bottom, that is not the mass number. Yes, I'm just going to do that move to illustrate that point. That is not the mass number. That is the atomic mass, which a lot of times people get confused because it is very similar sometimes to the mass number. But when you're asked to calculate the mass number, the atomic number, the number of protons, electrons, neutrons, they are all positive whole numbers. And if you look at all those numbers underneath the symbols on the periodic table, most of them are not whole numbers. Most of them are nowhere near a whole number. And those are, again, are the atomic masses and not the mass number. So if you wanted to know the number of neutrons, you would take the mass number, which is the top number, minus the bottom number, which is the atomic number there. So A minus Z would give you the number of neutrons. Every element has protons, electrons, and neutrons except for hydrogen. Hydrogen has a proton and an electron. It does not have a neutron. So hydrogen is the only sort of example element that does not have all three. Pretty much everybody else will have those three subatomic particles. So this little table here demonstrates some of the symbols that we commonly see in nuclear chemistry. And here's a couple more here to begin with that are maybe newish symbols to you, hopefully not so new. But sometimes to represent a proton, people will use the P and the 2 1s, or because really a proton is a hydrogen, people will sometimes use the hydrogen with the 2 1s to represent that. A neutron is a little n with a 1 on top and a 0 on the bottom there. And that's a very common symbol. And then you can see our symbols for electron, positron, and alpha particles, as we talked about. Again, you can see the electron and the positron will pretty much have the same symbols. So like I said before, they definitely will let you know which one they're talking about. And if you do not see a positive or a negative included, it's probably safe in most cases to assume it is, again, that electron, or really most people don't call it electron. They call it obviously a beta particle. Yeah. Now, depending on the type of radioactive particle that is coming off, especially if you ever do anything with radioactivity or work with something that's radioactive, it's always good to know what type of emitter it is. So there's two or three common words that you sometimes hear in nuclear chemistry. And one common word is emitter, or it's emitted. So if something is emitted, or it's a alpha emitter or a beta particle emitter, what that means is it's being given off. And what that means is that particle will be found over here on the product side. Now, if you bombard something, which is another common word, or even like our electron capture, what that means is that particle would be found on the reactant side. So it's like it's being added in. So those are the three sort of common words that you hear a lot in nuclear chemistry. If you bombard or you do an electron capture, you would put that particle on the reactant side of the equation. If it's being emitted or it goes through some type of decay process, like an alpha decay process or something like that, those particles will end up on the product side of the arrow. Now, depending on the type of emitter it is, it can penetrate at a different depth, depending on the type it is. Whoa, look at that. That's like sound effects there. There we go. So I think you can kind of see it, but we can see here that the alpha particle will penetrate 0.01 millimeters into tissue. The beta particle is next, which is here about 1. And the one that could go the furthest, as you can see here, is our gamma that can penetrate the furthest in terms of those particles coming off, which is why, again, if you are working with something that is radioactive, it's very good to know the type of particle that's being emitted, because it does require different types of protective devices. For example, if you're doing something that doesn't travel very far, perhaps all you need is some gloves and maybe a lab coat. You're doing something with gamma emissions, you might need some lead, some shields, and all that to sort of protect you as well. So it's really important to know if you ever do start working with something that's radioactive or has anything to do with radioactivity to, really understand what type of radioactive particle you're dealing with. Again, they're not all the same in terms of how far they could penetrate, as we'll talk about as well. Obviously, your time you spend around it is also very critical into any type of damage that could occur. Unfortunately, sometimes people don't always tell you all the important information. So sometimes you might have to determine that for yourself. And I would highly recommend that if you do find yourself working with anything that's radioactive. Here again, just some more of those symbols in case you missed the first 32 that we looked at. So let's talk about actually how to balance these nuclear equations. And balancing nuclear equations is different than a traditional chemical equation, again, because in a chemical reaction, as I mentioned, you do have that conservation of elements. So like we know when we balance an equation, a chemical equation, we put those coefficients in front of everybody. And that means, again, if we started with those 4 carbons on the left-hand side of the arrow, we should have a grand total of 4 carbons on the right-hand side of the arrow. And that is definitely not the case here with our nuclear reactions because, as I mentioned, we don't have the conservation of elements. So actually, the elements that we start with become new elements at the end, and we don't have that conservation. So that makes these guys a little bit harder to balance. And I'm actually just kidding. They're actually a lot easier to balance, to be honest with you. You pretty much just need to be able to add. So calculator is good sometimes for this. And really to have a balanced nuclear equation, there's really 2 things that you have to look for and make sure of. And the first thing is we should have a conservation of the mass number. And what that essentially means is when you add up all the mass numbers, which is all those numbers on the top there of the symbols on the left-hand side of the arrow, and you add up all the numbers on the right-hand side of the arrow for the mass number, they need to equal the same number. So if we look at this example here, this is a balanced nuclear equation. On the left-hand side, we have 235 plus 1, that is 236. And on the right-hand side, if we add up all the top numbers, we have 138 plus 96, and we do have 2. We would take the coefficient here and multiply it by 1, so that would be 2. And that also should be 236 on the right-hand side. And the second thing that has to happen when you're balancing a nuclear equation is you need to have the conservation of the atomic number, which is our guys on the bottom. So if we look on this example on the bottom left, we have 92 plus 0, which is 92 on the left. On the bottom right, we have 55, 37, and 0, which is also 92. This again would represent a balanced nuclear equation. So typically speaking, one way that you'll sort of see these is, for example, we'll say something was missing. So let's say you had this equation and this guy was missing. And you wanted to figure out, what was the missing sort of element. And the thing that tells you the element, right, is really your atomic number. So the approach that you would take is you would look on the left-hand side and go, I got 92 for my atomic number on the left. On the right-hand side of the arrow, I got 37 plus 0, which is 37. And if I take 92 minus 37, that gives me 55. And that would be my missing atomic number. And because the atomic number can be found on the periodic table, you would then go to the periodic table, you would find number 55, and obviously it should show you cesium as its symbol. And then all that would be left is to figure out the missing mass number, which is our number on top. You would do the same thing. Left-hand side, we got 236. Right-hand side, we have 96 and 2, which gives us 98. If I take 236 minus 98, gives me 138 as my missing mass number, which would go here. So one sort of way you'll see these sort of equations is something will be missing. And the best approach is to figure out the missing atomic number first, and then figure out the missing mass number. Now, in most cases, it probably will be an element from the periodic table that's missing, but it may not be an element. Remember, it could be something like a particle, like a neutron or something like that. So if you come across something that has kind of a weird number for the atomic number, like a 0 or a -1 or something of that nature, what you may actually be seeing is a particle that's missing in the equation. So I would say probably 9 times out of 10 it's going to be an element, but it could technically be a particle that's missing. So balancing nuclear equation is pretty simple. You just need to add up all the mass numbers, make sure they're the same on each side, add up all the atomic numbers, make sure they're the same. And really your best friend here is your periodic table while you're doing this. So let us take a look at this one together just to kind of see how we do it. So we have 212PO there, decays by alpha emission. Write the balanced nuclear equation for this decay. So the first thing we want to start with is our isotope here, which is PO212. Again, that 212 is the mass number. We could go to the periodic table and find the atomic number, and if you do so, that is number 84 there on the periodic table. The words here are important. We have alpha and emission. Emission means that my alpha particle is going to be on the product side. And again, you could represent that alpha particle two ways. You could use the alpha symbol, or if you like, nothing wrong with using the helium symbol. So you can use that as well. So we do want to find kind of what's missing here, if you will. So we'll start with the atomic number. On the left-hand side, my atomic number is 84. Right-hand side of the arrow is 2. So 84 minus 2 is 82. That is my missing atomic number, which goes bottom left. We then go to the periodic table and we look at number 82, and that is our good friend lead. And now what is left is our mass number, which is the top. So we take our 212 on the left-hand side, or 4 on the right-hand side. 212 minus 4, 208. It looks like a winner there. 208 would be it. And that would represent our balanced nuclear equation. Mass number on the left and mass number on the right equals each other, 212 on both sides, and 84 for the atomic number on the left, and 84 for the atomic number on the right. Any questions on any of that there? So this is another way that you may be asked to write nuclear equations. Again, you kind of give it in words, and that's where those words that we were talking about earlier, again, if it says something about emission, or honestly, if it doesn't even say emission, it just says it decays through alpha decay, that probably also means emission. Or if it says bombarded by a particle or electron capture, those guys would be on the reactant side. All right, so let's just talk about, again, some of the major differences that we did talk about here earlier between chemical processes and nuclear processes. So as I mentioned, really our chemical reactions deals with electrons, bonds being broken and made, and that's all electrons, right? So that's all those particles that are flying around the nucleus. Really no change in protons, no change in neutrons. And it is, as I mentioned, the protons that determines the element that you're dealing with. So obviously, if we don't change anything in the nucleus, we would obviously have that conservation of elements like we do see in a chemical reaction. Now, in a nuclear reaction, it is all about that change that occurs in the nucleus. So we're changing protons to neutrons, neutrons to protons, blah, 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 blah. And that means as we change those protons, we are changing the elements. So we definitely do not have that conservation of elements. Also why, as we will see and talk about, a nuclear reaction compared to a chemical reaction, there's quite a difference in terms of energy involved. Because obviously, if you're getting into that nucleus, it requires a lot more energy to change those protons and neutrons into something else than it does when those electrons are flying around. And that's why nuclear reactions usually will generate a lot more energy than any exothermic chemical reaction you could think of, which is also why we'll talk about also in this chapter, we do use nuclear energy for like nuclear power plants and stuff like that, right? It generates a lot of energy and it can be very useful in that sort of aspect. So let's take a little closer look at what is really happening here in in these sort of beta decays and positron decays and so forth. So the first thing here is our beta decay. And again, the beta decay means that our beta particle, which is right here, is going to be given off again on the product side. And if we look at the atomic number here, we're actually increasing the atomic number because 7 and minus 1 is 6. So you actually have to go up in terms of the atomic number here. 14 and 14 on each side, 14, 0 is 0. For our purposes, you don't have to worry about these neutrinos here. You can kind of just think of them as, and again, you don't have to worry about them or anything like that, but they have basically mass number is 0, atomic number is 0, sort of like some mass that will be converted into energy along the way. They're, again, known as sort of neutrinos, and we don't really get too much into them, so you don't have to worry about them. So if you want, you could even, for our purposes, not even worry about them. You could kind of get rid of them. You don't have to include them in any reactions or anything like that. So what is really happening when we go through this beta decay? We decrease the number of neutrons by 1, and we increase the number of protons by 1. So basically what's happening when we go through a beta decay is a neutron that's in the nucleus, obviously, is being converted into a proton and also given off that beta particle in that process. And that is why we are technically not changing, the mass number doesn't change, because let's just sort of follow the process. Doesn't really happen exactly like I'm going to show you here, but just so you could kind of follow what's happening. So what ends up happening is in this process, as we go through this beta decay, we're going to take away a neutron, right? And the neutron would be up here in our mass number, which is neutrons and protons, which technically would drop us to 13 and 6, right? But as that neutron goes away, it makes a proton, which would also be added to the top number and the bottom number, right? And that would then take us back to 14 and 7, which now moves us from carbon to nitrogen, yeah? And in the process of doing that, another particle is made, which is our beta particle. So not 100% the way that happens, but just so you figure out, well, how come like the mass number didn't really change? It technically did, but we're replacing really a neutron there with a proton, if that sort of makes sense. And obviously, as we do, that proton goes into both spots, the mass number and the atomic number. And obviously, as we change the atomic number, the element would change as well. So when we do a positron decay, a similar thing happens. We have, again, our positron particle on the product side. And basically what's happening is we're increasing the number of neutrons by 1, decreasing the protons by 1. So essentially what we're doing is we're taking a proton in the nucleus. It is going to be converted to a neutron, and in that process going to give off that positron. And the same thing happens again if we just kind of follow the numbers. As this process occurs, we're going to lose a proton here, which means we would go to this, right? Which now would take us back to 5. But as we lose a proton, we then gain a neutron, which would be added back to here. This also should have dropped to 10, right? Because it came out of both places. And when we add it back to here, we get back to our 11 in that case. Again, because the proton would have came out of both places, as the top number is protons and neutrons. And so again, a positron really converting a proton into a neutron, and the process of that will release a positron particle. Now, electron capture is one of those few ones that will put the particle on the reactant side. So because this is an electron capture, we actually see the electron on the reactant side. And when we do that, if you just kind of add up the math here, 1 minus 1 gives you 0, and 1 on top, and that's basically a neutron. So we're going to increase the neutrons by 1. We're going to actually decrease the protons by 1. And again, this is the same reason that we do not see a change in the mass number, because as the protons go down, mass number goes to 36, but then we replace it with another neutron, which means it goes back to 37 in that example, that first example there. And obviously, as we decrease the proton, our atomic number goes down by 1 to 17. The biggest sort of change that occurs is our alpha decay. And in an alpha decay, again, the atomic number changes by 2, and the mass number changes by 4. This is fission, and fission is the process where an unstable nucleus, for example, breaks apart into 2 new nucleuses and forms some neutrons. A lot of times that would also involve some energy that occurs. So spontaneous fission is a spontaneous process where you do have this unstable nucleus that occurs, and it will want to break apart. Now, for example, in this example on the bottom there, it won't always break apart into 2 of the ions, for example. It may break apart into 2 other elements, but it usually will break apart into at least 2. Usually will generate some neutrons and some energy associated with that. You could actually cause that to occur, and we'll talk about that later in this chapter, and that is caused by what's sometimes referred to as transmutation, which basically means you shoot a particle at a stable nucleus, and it's like, thank you very much, I'm a little unhappy you just shot a particle at me. It becomes unstable and kind of goes through this fission process. So you could kind of start a fission reaction by bombarding a stable nucleus with a particle like a neutron or something like that, and it can kind of kick off that process where that isotope will split apart into new nucleuses and some particles. Here's a table similar to the one in your book that just sort of describes the different reactions that we just talked about. So why don't let's do this one here together, and then you'll have some that you could do, I think. So write the nuclear equation for the positron emission for potassium-40. So why don't you take a moment and write the balanced nuclear equation. Again, helpful for you would be a periodic table at this point. So give it a try, and then we'll talk about it. Okay, so let's take a look at this and try to see. So potassium 40, and remember that when it is written like this is the mass number. So we would start with the potassium with the 40. Remember that if it is not given to you, you can use the periodic table to figure out the atomic number, which in this case is 19. So we want to write the nuclear equation for a positron emission. So remember that our positron is either that symbol or that symbol. And also remember the other keyword here is emission, which means that that particle should be over here on our product side. So that means we do want the arrow. We do want our positron. Again, whatever symbol you want to use there, either one is perfectly fine. And now remember that the whole basis of balancing our nuclear reactions or equations is to make sure we have the same atomic number on each side total and the same mass number total on each side. So on the left-hand side, we have 19 for our atomic number, the bottom number. On the right-hand side, we have 1, which means if we take 19 minus 1, that will tell us that 18 is our missing atomic number, which is why we want to start with that, because we could then go to the periodic table, and we see number 18 on the periodic table is our good friend argon. Now, we also want to make sure that the top number or the mass number is balanced on both sides. And that's going to be a 40 on the left-hand side, 0 on the right-hand side, which clearly means 40 should go here. And that should represent our balanced nuclear equation. If you add up all the atomic numbers on the right, they equal 19. All the atomic numbers on the left equals 19. All the mass numbers on the left equals 40. And if you add up all the mass numbers on the right, it equals 40 as well. Any questions on that there? Okay, I think got a few more to go here. So why don't you give these a go? For each of these, please write the balanced nuclear equations for each of them and see what you come up with. Okay, so let's see how we're doing. So again, each of these we want to write a balanced equation. So each of them, uranium-238, neon-24. Again, those numbers are the mass numbers, which would go on top. So here we would have uranium 238. We could go to the periodic table and see that uranium is number 92 there. Emission is going to tell us that our particle is going to be on the product side, and that's the alpha particle, which is the 4 and the 2. Again, you can use the helium symbol. You can use the alpha symbol if you like. We're going to figure out our missing atomic number because that's going to help us identify the element. So that's 92 on the left, 2 on the right. So if we subtract those, that gives us 90 in terms of our missing atomic number. Again, going to the periodic table, we see 90 is TH. And for our mass number, we have 238 on the left. We have 4 on the right. So 234 looks like a winner. Any questions on that first one there? All right, so following the same approach here for our next one, we have neon that is 24 on top, the mass number. From the periodic table, we see neon is lucky number 10. Again, we're dealing with an emission, which tells us that the particle should be on the product side. And that beta particle, again, you could use either the E or the beta symbol to do that. And again, we want to figure out our missing atomic number. So here we have 10 on the left, minus 1 on the right, which means we actually need to go up to 11. 11 and minus 1 is 10. And number 11 there is sodium. And 24 on the top, 24 on the left, and 24 and 0 is 24 on the right. And that would be our balanced equation there. And continuing on, nitrogen 13 on top, 7 from the periodic table. Again, we have an emission, but this is a positron, which means that's going to be the positive sort of beta guy. That means on the left-hand side, we have 7 for the atomic number. On the right-hand side, we have 1, which our missing atomic number in that case would be 6. And that's going to give us carbon and 13 on top. Any questions on that one there? And again, remember the goal here is to balance the overall mass number on the left and mass number on the right, atomic number on the left and atomic number on the right. And we just read your questions here. So the first question, I think was involving this one here. So on the left-hand side for the bottom, we had 10. On the right-hand side, we had minus 1. So if you made it 9 over here, 9 and minus 1 gives you 8, right? And obviously that does not match. So because this is negative 1, you actually have to go to 11, and minus 1 gives you 10 when you add those together, and 10 on the left-hand side. So that's why that one there was 11, so that it matches. And because you have that negative 1, which means you actually need to go 1 more in terms of the atomic number. And to answer the other question that's there, yes, a beta particle and a positron, they do have the same sort of symbol, if you will. But the difference is a beta particle is negative and a positron is positive. That's why I sometimes call it a positive electron. But they do have the same symbols. And the difference, though, is, again, that's minus 1 for that guy, and this guy would be plus 1. So they definitely will indicate that it is the positron with some type of plus 1 or positive on there. If you just see straight out, just like I talked about before, if you just see the beta particle written, it is probably safe to assume that it is the negative version. But the beta particle and the positron are actually 2 different things. one is kind of like a positive proton, positive electron. I'm sorry, in the case of a positron. Other questions on that? Okay, so let's take a look at electron capture then. So electron capture, beryllium. You see what it says, right? It's Be. I think that's beryllium. I'll spit it out. So that's the mass number there, and the atomic number, which is 4. At least I could entertain myself. I think that's the important part, really. We have an electron capture, so this is going to be different. This is going to put our electron on our reactant side. So that's one of the 2 ways you can kind of get a particle on the reactant side. Again, that electron capture, or again, if it says something like you bombarded this guy with this particle. So what we got going now is everybody's on the left-hand side. So we have 4 and -1 on the left-hand side. So this time you would actually add those together, and that would give you 3. And that would be the missing atomic number over here. And number 3 there is lithium on the periodic table. And if we add our left, we have 7 on the left-hand side. And now we need 7 on the right-hand side to balance it out. Not too difficult to balance these guys. Again, the periodic table is really your friend when you're doing this. And pretty much you should start with the atomic number, because then you could go to the periodic table and pretty much figure out what's missing. Any questions on how to write balanced nuclear equations? Okay, so let's see. What we're going to talk about now is actually stability, and one sort of way that we measure stability or try to figure out stability when we're talking about radioactive nuclides. And by the way, nuclides are sometimes what is referred to when we're talking about sort of these radioactive isotopes, if you will. And one way is we could use what is known as the N to Z ratio. N is the neutrons, Z is the atomic number, or the number of protons. So this is the, this is the neutrons to proton ratio. And that's a pretty good measure of stability. And we could use that to help us decide if a isotope is going to be stable or not stable. So if we measure the N to Z ratio and we determine that it is too high, and we'll see what too high is in just a second, but if it is too high, what that will tell us is it is really not stable in that sort of configuration. And what's going to happen is some neutrons will be converted into protons, and it will go through a process known as beta decay. So if you measure the N to Z ratio and you feel it's too high, what will happen is that isotope will go through beta decay. And what that will do is move its ratio, is neutron to proton ratio, closer to a more acceptable and stable situation. Will it become perfectly stable after just the 1 beta decay? Maybe not, or maybe so. But it will definitely move it closer to being a more stable situation. Now, the opposite of that is if you calculate the neutron to proton ratio and it's too low, we will convert some of those protons into neutrons, and it will go through either a positron emission or an electron capture. And it can go through an alpha decay, but it's not as efficient, so we won't worry too much about that for here. So for us, it'll either do a positron or an electron capture. And you may ask yourself, why can it do both? So a good example of why it's okay for it to do both, or why it may do both, is what we see here. So that was beryllium 7, correct? So if you remember the last one that we looked at, which was beryllium 7, went through an electron capture, and we ended up with lithium, right? So that is an electron capture. If we took our beryllium and went through a positron emission, which would look like this. And if you wrote the balance equation, what you will see is if you perform an electron capture, or if you perform a positron emission, you end up with the exact same outcome. So as the example we just did, we first did an electron capture. We ended up with lithium with an atomic number of 3 and a mass number of 7. We ended up doing a positron emission, and we actually ended up with the exact same isotope as well. So if the ratio is too low, you have either of those options. If it's too high, it's going to go through a beta decay. Any questions on that? So how do we know if it's too high or too low? Let's actually take a look at what helps us determine that. And that's the best choice. Hopefully you can kind of see it. This is what is sometimes referred to as the valley of stability. Some books call it the belt of stability. And basically this kind of yellowish section here is pretty stable for most things. And again, that's what's referred to as the valley of stability or the belt of stability, whichever one you like. And it's basically the N to Z ratio. And basically what it says is if you have an atomic number that goes from 1 to 20, an acceptable N to Z ratio is 1. If you have an atomic number that goes from 20 to 40, the acceptable ratio is 1.25. And if you have one that goes from an atomic number of 40 to 80, the acceptable ratio is 1.5. And pretty much anything above 83 is going to be radioactive, so you don't have to worry about it. So these are the cutoffs that we could use when we're calculating the N to Z ratio to determine whether or not it is going to be stable or unstable. So when we talk about being too high, when we're talking about being too high, that ratio is out this way. And when it goes through that beta decay, it's going to move that ratio closer in, as opposed to if we're too low, it's like on this side of the yellow. When we go through that positron emission or electron capture, it's going to move the ratio closer to that valley of stability or that belt of stability, which is going to make it more stable. Will it be perfect after 1, like I mentioned? Maybe not, or maybe so, but it should be moving in the right direction towards that valley of stability or the belt of stability. All right, so a couple of things about these cutoffs. We are in our class, to make sure it's pretty straightforward on a test or something like that, it is either that number or it is too high or too low. So there's no kind of grayish area. And what I mean by that is, as you can kind of see, for example, this cutoff ends at 20, but this one starts at 20. So there is sometimes people, when they use these cutoffs, sort of a grayish area. They're like, well, atomic number is like 20. It's like it's above 1, but less than 1.25. It's probably okay still. It's still probably stable. So it creates a lot of sort of gray areas. Again, as you go from 20 to 40 or 40 to 80, there's that 40-ish area that's sort of grayish as well. So to cut that out, just to make it simple, and again, just for our class, and you may see something different in the book or something like that, but for tests in our class, just to keep it simple, we're going to make those pretty hard cutoffs. And again, what I mean is either it is like the 1 for the ratio, or if it's not 1, even if it's just slightly above 1, it's too high, or if it's slightly below 1, it's too low, just to keep it sort of simple ways to remember these. But I will tell you, in reality, some people, there are some of those gray areas that sort of happen between the different cutoffs, between 1's okay and 1.25 is okay and 1.5. Any questions on that? So let's take a look at how this actually comes into play. So I'm going to give you a second here to try to figure it out here. If we have magnesium 22, is it stable? And if it's not stable, what type of decay process will it undergo? And while you're at it, why don't you write the equation for the decay process it undergoes? So take a minute or so and try to figure out what's going to happen here with our magnesium 22. Okay, so let's take a look. So really we're looking at stability and we want to figure out our nitrogen, our neutron to proton ratio. So again, our magnesium is 22 is the mass number. The atomic number is 12. So remember, if you take the mass number minus the atomic number, that gives you 10, and that is the number of neutrons, right? So mass number minus the atomic number gives you the number of neutrons. Obviously, the atomic number here is the atomic number and the number of protons. So if we take 10 divided by 12, that gives us the grand total of 0.833 as our neutron to proton ratio. This is a guy with an atomic number of 1, which means its acceptable ratio is actually atomic number of 12. I'm sorry. Its acceptable ratio is actually a ratio of 1. So a stable ratio for this guy is 1. When we compare these two numbers, we see that the 0.833 is lower or too low, right? And when that ratio is too low, it is going to go through one of two things. It can go through either a positron emission or an electron capture. Remember, they both end up the same spot. So if you were to write that equation, it would be 22 magnesium given off our positron, and our missing atomic number in this case would be 11, and our mass number would be 22. Atomic number 11 on the periodic table is sodium. Again, it could also go through an electron capture, which will end up giving you the exact same product. So again, for this type of situation, you do have a couple of choices. They both get you to the same end result. So that would be the balance equation for the reaction that would take place as this guy would go through the decay process. So let's see, does it actually help us? So right now, just randomly, he's sitting kind of here, if you will, too low underneath that belt of stability. We have now formed sodium 22, which means the N to Z ratio of our sodium 22 is 22 minus 11 is 11 for the neutrons. And our atomic number here is 11, which means we went from our original guy that had a ratio that was too low. By going through this decay process, we actually, in this particular example, actually hit the perfect ratio by going through one of those two processes. As I mentioned before, it won't always be that way. You won't always hit the perfect ratio after you do the first decay process. You don't have to continue to do it until you hit it perfect, but it definitely should move you in the right direction. So as you can see here, it definitely did move us in the right direction. Question on that? All right, well, that feels like enough torture for one day and one afternoon. So a couple of reminders. So let me ask your question before I get to that. So we knew that the N to Z ratio needed to be 1 for that particular case because the atomic number was 12. And if you look on the slide that we were on just before that, anybody that has an atomic number 1 through 20, the acceptable ratio is 1. And then if you go from like 20 to 40, the acceptable ratio is 1.25. And then like 40 to 80, in terms of the atomic number, the acceptable ratio was 1.5. So because magnesium had an atomic number of 12, it fell into that acceptable ratio of 1. Other questions on that? All right. Well, like I was saying, that looks like enough torture for one day. Yes. A reminder that 1 week from today is our next exam. So make sure you just take some time out to study and all that good stuff. We will continue on next week with some more labs and stuff. So make sure you take care of the pre-labs. Other than that, have a good holiday. Have a nice weekend. I will see you Monday. We are officially ending the lab on time, an hour and a half early. All right. Have a good rest of your weekend and all that. I'll see you Monday.